So thanks, Andrew. I'd like to present a line of work here that's developed by us and also other groups that focuses on the integration of two of the, let's say, major fields of cognitive modeling, which are reinforcement learning on the one hand and evidence accumulation models on the other. And I'd like to start by providing a motivation for this idea of integrating these models. I'll begin with presenting a brief comparison of the fields. So let's begin with reinforcement learning, where a typical task paradigm is this incremental learning task, where a participant is presented with these abstract symbols, and the participant is informed that he needs to make decisions and gets rewards depending on his choice. And then he's instructed to discover by trial and error which of the abstract choice symbols are most rewarding in the long term. And typical models here assume that the participant keeps track of a representation of the value of each choice. And this representation is the Q value, which is updated after every choice according to this delta rule, which essentially just says that the Q value in the next trial equals the current Q value, plus some sort of difference, weighted version of the prediction error, which is the difference between the reward and the expected reward. So using this rule, what you can do is you can get the Q values for every trial in the experiment, and then you can translate Q values into choice probabilities using a choice rule that's called softmax. And then what you can do then is compare the empirical choice probabilities to the model's predictions, and if the model fits well, then you can interpret the model's parameters or the Q values or the prediction errors. On the other hand, we have evidence accumulation models where also choice tasks are used, but they don't typically have an explicit learning component in them. So a typical task is this random motion task, which has been mentioned before, where the idea is that a subject is presented with this cloud of randomly moving dots, which is subset moves coherently to the left or to the right, and the subject needs to decide what the dominant direction of motion is. Now here the models really focus on the decision process, which is conceptualized as evidence accumulation to threshold. So this is again the DDM, which assumes that the participant accumulates this noisy evidence until one of the two thresholds is reached, at which point the subject commits to its decision. And then if you repeat this over and over again in an experiment, the model then predicts response time distributions for correct and for incorrect answers. And then again, you can compare these predictions against the empirical data, and if it fits well, then you can interpret the model's parameters. So from this view, if you compare these models, then you can see that they're both applied to choice tasks, but they focus on two distinct but completely complementary cognitive processes. We have reinforcement learning that focuses on learning by trial and error, and we have evidence accumulation models that focus on the formation of choice based on some abstract notion of information. And as such, reinforcement learning offer a formal model of learning, but don't offer a process account of choice, and they ignore response time distributions. And evidence accumulation models do the opposite. They don't offer a formal account of learning, but do offer a formal account of process model of choice and of response time distributions. So what we're trying to do here is to make use of this complementary nature and, in a sense, try to get the best of both of these worlds. So the promise here is to get a single model that offers process accounts of learning, process accounts of choice, and it's informed by and can also explain all the behavioral data that we have. So these are choices, response time distributions, and also the changes in choices and response time distributions that occur due to learning. All right, so this is what the general approach looks like. This was developed by Mats Pedersen and Lara Fontanesi a few years ago. We assume that the participant is presented with these abstract choice symbols, and like in reinforcement learning, we assume that each of these has an associated Q value, and now we're going to assume that these Q values drive an evidence accumulation process. So let's just begin again with the DDM. We can, for example, assume that the DDM's drift rate, so the mean speed of evidence accumulation, is some sort of function of the difference in Q values. So these Q values drive this evidence accumulation process until a threshold is reached and a choice is made. The subject receives its feedback, and based on the feedback, it can update its Q values based on this reinforcement learning simple delta rule. So the next time that the subject encounters the same choice, we again have a diffusion process, but now with a new drift rate because we have new updated Q values. Right, so this simple model is known as the RL-DDM, which just combines the simple delta rule with the DDM in this way. Right, so the first thing we did was an exploratory experiment to test how well this model can actually capture all patterns in the empirical data. And then I'm referring to choices and response time distributions. So what we did is we used the same simple instrumental learning task, where again, the participants were just presented with these abstract choice symbols over and over again. After every choice, they receive their feedback. And the reward probabilities of feedback differ between 4 what we call stimuli sets. These are just pairs of abstract symbols. And since we have these varying feedback probabilities, we have effectively created 4 difficulty conditions. Right, so this is an overview of the results. In all these graphs, the white lines represent the data averaged across subjects. The yellow shaded areas are the 95% credible intervals, in this case of the RLDDM. On the x-axis, we have trial number, which we vented to 10 bins. And on the y-axis, we have accuracy on top, correct response times in the middle, and error response time in the bottom graph. So the first thing we can see here is that participants learn, right? So accuracy increases over time during the experiment, which is entirely expected, but it's nice and reassuring to see. And the RLDDM is able to capture this learning-related increase in accuracy quite well. This is pretty much on par as what softmax does in accuracy, so that's quite good to see. But the quality of fit of the response times is a little bit more troubling. So as Andrew already explained, in the lower line here are the 10th quantile, we have the 50th quantile, the median here, and the 90th quantile here. And what we see is that participants get faster because they learn this task, and the RLDDM is able to capture this median RT reasonably well. But it strongly overestimates the 90th quantile RT and strongly underestimates the 10th quantile RT, which implies that the RLDDM consistently predicts more variable and a higher skewness of the response time distribution. So it captures one aspect of the RT distribution well, that's the central tendency, but it misfits the shape of the response time distribution. And this goes for the entire experiment across the entire, across all trial bins, and also for both correct and for incorrect answers. So we consider this a bit of a weakness of the RLDDM because apparently it doesn't fit all aspects of the response time distribution as well, and we aim to improve upon this. So this RLDDM so far simply combines the simple delta rule of reinforcement learning with the DDM of evidence accumulation models, but there are many other potential RLEAMs, which has to do with the fact that in both of these fields we have a lot of individual models. And given that we're combining these two fields, we get this combinatorial explosion of potential RLEAMs. And so what we did specifically was to focus on the evidence accumulation model part. And the reasoning is that the misfit of the RLDDM appears to be in the description of the response time distributions and not as much in the learning-related changes over time. So we assumed this simple delta rule throughout, and then we set out to test 2 more evidence accumulation models, which are to some extent generalizations of the DDM. The first, or actually the second model we used was based on this racing diffusion model architecture, where the idea is that each choice option has a corresponding accumulator. They both race towards a common bound. They're one-sided diffusion processes. And in this specific model, we assumed a quite simple mapping between Q values and drift rates. So each drift rate is a simple function of an intercept or an urgency term plus a weighted version of the corresponding Q value. And then the second alternative model made use of this advantage framework that Andrew already introduced. We again have 2 accumulators and we have 2 Q values, but the mapping between Q values and the accumulators follows the advantage framework. So each drift rate is a function of 3 terms, namely the intercept, the advantage term, and the magnitude term. So this last model appears a lot more complex than the other 2 models, but all the complexity is really in the structure of the model. So the mapping of Q values to drift rates. It still only has 6 free parameters, and it remains fully recoverable even with relatively low trial numbers. So what we did here was to fit all these 3 models to the data of experiment 1, and then performed formal model comparisons. On the left, we have the RLDDM again. In the middle, we have the RLRD. On the right, we have the RLARD. So on the right, we have the advantage framework. And the first thing to note here is that both the racing diffusion models are able to capture the response time distribution a lot better than the RLDDM. So both of these diffusion model, racing diffusion models don't overestimate the variance or the skewness of the response time distribution. But the RLRD overestimates the response times of the early trial bins a little bit, but the more strong misfit is in the accuracy. So this model really strongly underestimates the accuracy throughout the entire experiment. The RLARD, on the other hand, fits the accuracy about as well as the RLDDM, plus it offers a very nice description of the entire response time distributions. And also, if you formally compare these models with the BPIC, for example, this is the winning model. So given this new candidate model, what we did next is to test how well the RLARD can explain the effect of difficulty. So given that we had 4 difficulty levels in this experiment, which differed in the reward probabilities, these are shown in the columns from hard on the left to easy on the right. And the data show the expected pattern that when it gets easier, such as get better, they have higher accuracy and they get faster. And this model is able to capture almost all of these effects quite well, except for one part, which is the early trial bins in the easiest condition, where the model underestimates accuracy. And this likely has to do with the fact that 31% of the participants reached perfect accuracy in this condition. So they probably just had a lucky first guess on the first trial of this condition, and then stuck with the choice. So they didn't follow a real sort of update rule. But for the rest, this model is able to capture this data very well. And it's perhaps interesting to emphasize here that there are no free parameters between these conditions. So the entire effect of difficulty is explained by the differences in Q values and the mapping of Q values to drift rates. Right, so given that we have this new candidate model, we then set out to do 2 more experiments to see if it can also capture well-studied effects in the literature of reinforcement learning and evidence accumulation. The second model had a speed trade-off manipulation. So prior to each trial, participants are instructed to emphasize either response speed or response accuracy. And then also their feedback depends on the response time. So if they're too slow, then they'd never get a reward in order to incentivize responding fast. In the third experiment, we used a reversal learning paradigm, where halfway through each block, the reward contingencies flipped, such that the choice that was optimal before the reversal was actually suboptimal afterwards, and vice versa. And the participants were never informed that this was going to happen, so they had to figure this out by trial and error. So let's first have a brief look at the results of the SAT experiment. What we did here is apply a model comparison between several RLDDMs and several RLARDs, which differed in the parameters that were allowed to vary between conditions. What you're looking at are the winning models, so the winning RLDDM on the left and the winning RLARD on the right. The data again show the expected learning effects, so participants get better over time, they get faster over time, and also the expected speed trade-off effect. So they are more accurate and slower in the accuracy condition compared to the speed condition. And both models are actually able to account for the speed trade-off effect fairly well, except that the RLDDM again overestimates the variance and the response and the skewness of the response time distribution. And this misfit is so strong that even the worst fitting RLARD still fit better than the best fitting RLDDM. So that's quite a strong effect. And this is the reversal learning paradigm, where on the x-axis I have trial number now, so not trial bin, but trial number relative to the point of reversal. So trial 0 is the first trial at which the reward contingencies flip. And the data again clearly show that participants learn, and then very quickly after the point of reversal, they change their behavior and they switch to the other choice option. In fact, they change their behavior so fast that both of these models and also softmax actually underestimates the speed of change in choice probability, which likely has to do with some of the participants figuring out that there are these reversals and then using some sort of model-based strategy to change their behavior. The other aspect in the data here are the response times, where you can again see the participants speed up to the point of reversal, then slow down actually a little bit after reversal, and then speed up again. And this sort of post-reversal slowing is also captured quite well by both models. But again, the RLDDM overestimates the variance and the skewness of the response time distribution. All right, so very quickly, So far, up to this point, we showed that the RL-ARD captured various effects in binary decision-making. So we wrote this down, and we got peer reviews which challenged us to test whether this model can also capture multi-alternative choice. So we designed an experiment with 3 choice alternatives per trial, and we had 2 within subject manipulations, which are difficulty and magnitude manipulation, with difficulty referring to the difference in the reward contingencies between target and distractors, and magnitude to the sum of the reward probabilities. This is just to briefly recap what the 3 alternative RL-ARD then looks like. We have 3 choice options, we have 3 Q values, but we have 2 accumulators per choice option, each accumulator accumulating evidence for 1 pairwise difference. And we assume, like Andrew explained, that the choice option for which both accumulators have reached a threshold first is the one that wins and determines the response time. But even though we have a much more sort of complex looking network here, there's still only 6 free parameters. And also this model remains well recoverable even with relatively low trial numbers. Right, these are the results. We have 1 column per condition, easy and hard referring to difficulty, and high and low referring to magnitude. There were some interesting interactions between difficulty and magnitude. I don't really have time to go into these in detail, but the RL-ARD was actually able to accommodate all these complex patterns in the data quite well, including a rather strange observation that the fast quantum RTs and the error distributions become slower over time, which is rather interesting given that participants learn, so you expect them to get faster. But in this case, in the error RTs, they actually get slower, which is captured quite well by this model. Right, I'm going to start wrapping up now. I hope to have shown that RL and average accumulation models study highly complementary processes, and that joining them into these integrated models can provide mutual benefits, if you wish, which is a single model of response times, of choices, and of the learning-related changes in response time distributions and choices. And they're constrained by all the available data. There are many potential models in this class, but we offer 1 candidate model, which is the RL-ARD, which captures the effective difficulty of SAT, of reversals, and of multi-alternative choice. So if you're interested in this work, we've recently published 2 papers on this, the first being more of a perspective, the second being the empirical work. Also check out Mats Pedersen's and Lara Fontanese's papers on this. They're also very good. I'd like to briefly thank everybody at the IMCN group, including Birte, Annie, Andrew, and Nick, and thank you for your attention.
Okay, thanks very much, Stephen. We've got time for a couple of questions. I'll get through all of them. Asked, did you consider versions of the DDM with trial-to-trial variability? And if so, did it was it able to fix up the problems? And related, Johannes asked, can you explain why it is, or what's causing the DDM to misfit?
Yes. So the first question, we also tried including between trial variabilities in the DDM. It didn't help. That's sort of the short answer. But also conceptually, one of the things that we're trying to do is trying to explicitly model the reasons behind between trial variabilities. So it would actually be, we actually think it's beneficial to try to get rid of these sort of distributions that determine your between trial variabilities, but instead offer a process account of what these between trial variabilities are caused by. And in this case, that's learning. But even if you include them, the misfit doesn't go away. The only thing that can solve the misfit is between trial variability in in non-decision time. But then you need very large non-decision time variabilities in order to misfit this. And even then, the RL-ARD still fit a lot better. The second question was why does the DDM misfit? That's something I've also been struggling with for quite a while now. It appears that there's some sort of urgency-like mechanism going on, but I don't think that's a very sort of satisfying answer, and because it just raises the next question, and that's why is there such a strong sense of urgency then in these tasks compared to, let's say, a random motion task? And I don't know that yet, and I think this has been observed before, that the DDM can misfit value-based decision-making in general, with the same sort of pattern of misfits, namely this overestimation of variance and skewness. But the exact sort of cognitive reason for this, I don't know yet. which I did.
Okay, thanks very much, Stephen. That was a great talk.